All right, let's continue then. So we are still talking about this, I often call it functional form of the multivariate Gaussian, which we have seen now. Looks like this. It's the minus. And we talked about most of the components so far, and what we haven't talked about is the inverse here of a matrix, because I'm telling you now that sigma is a matrix, and another thing related to sigma, namely namely the determinant. So sigma is a matrix which is n times n dimensional, and I usually call it the covariance matrix parameter. And we will look a little bit closer at it, but make sure you don't confuse it with a sum symbol. So it's not the sum symbol, it's a sigma for a matrix. And there are two things that show up with this with respect to sigma here. First, its inverse, and second, determinant, as I just said. And so we talked about matrix multiplication before, but we didn't talk about matrix inversion. And matrix inversion is actually, if you want, a little bit more of a big and more complex topic compared to matrix multiplication. So I will basically just try to give you an intuition about matrix inversion, and because it would be way too much to cover matrix inversion in any depth, really. So the way I will do that is appeal to your intuition that you have from school. So let's talk about matrix inversion now. So assume we have something like this. So an equation of this type, where A is n times n is an n times n dimensional matrix, and X is n times p dimensional matrix. What do you know about Y? So what's the size of Y? N times P, yeah. Because the inner ones need to be addressed. Now let's simplify that in terms of looking at a scalar equation. Yeah, so we're now forgetting matrices for the moment and thinking about scalars. So that would be something. So I'm using smaller case letters now. So A times X equals Y. And we did something, I think, last time already, where the aim was to isolate the X, I think was the like we called last time. So think of, in this case, as an equation like that, where A and Y are known, but X is unknown. Yeah, so A and Y known, and X is unknown. And then you remember from school how you would solve something like that. So what would you do to get to the X? Maybe I take one, because now we have multiple versions.
Divide by 2.
Divide by 2. Is there another way that you can express divide by 2? Yeah. So one could either write something like this, divide by 2, or, and this is more in the spirit of matrix inversion, multiply by 1 over 2. And of course you want to do that to both sides. So you would want to do 1 over 2 times 2x equals 1 over 2 times x, and then you would get x, especially you would get here 1 times x and 6 over 2, so 3. So the important thing that happens here is that you multiply both sides by what is called the multiplicative inverse of something. So maybe let's do that more abstract here. So what you just propose to do is to multiply both sides of the equation with 1 over a. And this is how you get to your result, because then here you have 1 over a times a, so which we can also, if we want, you can also write that as 1 to the power of minus 1, a to the power of minus 1 times a x 1 over, yeah, that's also fine, but we can also write that as this. And then we get, because 1 over a times a, or a to the power of minus 1 times a is just 1, we just get x equals a to the power of minus 1 y. Yeah? So, and the whole thing works because this is 1. Now this a to the power of minus 1 is also known, so that's the 1/2 here, as the multiplicative inverse, Jesus. And the thing I want to get at with this is that for matrices, these kind of multiplicative inverses are also, yeah, they're not necessarily defined, but they are also a concept, and that means that one can, under certain circumstances, which we will not discuss in the course, at least for square matrices, or let's say only for square matrices, because if you're not dealing with a square matrix, then you get things called pseudo-inverses, so that's something different. So for square matrices A, one can also, under certain circumstances, have a matrix A to the power of minus 1, that if you multiply with a, so we are now back at this equation, on both sides, you essentially, to the power of minus 1, you get only x. Yeah. So you can compute this kind of matrix a minus 1, so that's also a matrix. It's also a square matrix, so a to the power of minus 1 is also square. N times n. You can, if you're lucky, you can compute that, and if you multiply that with a, then a goes away if you want, so you can isolate the x, which is here now, of course, matrices. In fact, it's essentially equivalent to what's happening here. So what you actually get if you multiply a minus 1 times a is what is called the identity matrix, and that's actually important. So the identity matrix In is the matrix that is square, so it's n times n, and it's essentially defined by the property that it only has ones on the diagonal and zeros everywhere else. Yeah. So that's kind of the general way. So let's maybe I3 would look like this. Yeah. Oops. Now I changed my modus here. It's not that good. Yeah. Oh, no, I didn't. So that's I3, the identity matrix. So just once on the diagonal, zeros everywhere else. And you might want to check for yourself at home that if you multiply a square matrix by the identity matrix, then what you are left with is just the matrix X itself. Yeah. So this idea allows you to so the idea of a matrix inverse allows you to evaluate or solve these kind of equations for something that you don't know if you know A and you know Y. However, it is not necessarily. So first of all, it's a little bit different than from the scalar case, because there can be cases where you have a matrix A which is square and n-dimensional, but the inverse of which is not defined. So the inverse of a matrix is not necessarily defined. And then it's also not that easy necessarily to compute the inverse of a matrix. So I made some weeks ago already, I made a little video that explains how one can invert small matrices by hand. Small meaning something like 3x3 matrices, 4x4 matrices. If you have nothing else to do, maybe also 5x5 matrices. So I explained that there so that you can get a little bit of an idea of how matrix inverses can be computed. In real life, one uses a computer to compute inverses of matrices, and there are many clever algorithms that compute such inverses. So for our purposes, it's more important that you remember that if one multiplies a matrix with its inverse, if this inverse is actually a well-defined thing, then you get the identity matrix and you can basically get rid of something like that. So the good news about the case that we are having here, so here the inverse of the matrix is actually not there to cancel something out or something. It's just there as a kind of a contribution to the function. We will use matrix inverses also to cancel out things when we talk about a maximum likelihood estimation. Here it just shows up. It doesn't want to cancel out something. Because this covariance matrix parameter here, the sigma, is a special matrix, which is called a positive definite matrix, it's also clear that if one goes into the theory of positive definite matrices, that this inverse actually exists. And then there are clever ways to compute the inverse of this. But this is what this symbol here means. So in a way, it's fairly analog to what we discussed earlier. So if you have 2 to the power of -1, that's 1/2. And here you can intuitively think something like, okay, this is 1 over the matrix sigma. So if you multiply it with sigma, you get 1, although this, of course, doesn't make any real sense. Yeah. So have a look maybe at the little video that I did on inverting small matrices by hand. Then you get a little bit closer intuition of what this matrix inverse is about. But yeah, you think of it as the multiplicative inverse, like essentially like dividing by a matrix, but that's not really an operation. Yeah, only multiplying with the inverse is defined. Questions about that or other viewpoints? No? You don't care anymore. Yeah, it's fine. Sorry. Good. This will be the last thing that is a little bit boring. Then everything will be just great. So the last thing that we need to talk about are determinants, because this here actually is the determinant of a covariance matrix. So, and again, this will be kind of a really fast-paced and superficial introduction to determinants. Actually, yeah, I wrote a little bit about determinants. It's not that clear whether determinants are actually that useful these days in mathematics, but they are still sometimes there. One can write 4 square matrices. So again, let A be a square matrix. So what determinants were used for is to actually determine whether equations like this have a solution or not. So whether one can actually invert this. And they are, determinants are, you can view them as functions. So let's use our new function notation here, that for square real matrices, map this square matrices on a single function, on a single value, sorry. So you take an A and you map it onto the determinant, which is here denoted with these bars. This is, although said there already, that's just a scalar. Yeah, so you have a matrix, you have an n by n matrix, so you have an n by n array of values. So, for example, 100 columns times 100 rows of numbers, and then you can compute its determinant, and the determinant is just a single number. So, what is this number? How is it defined? And that actually is. This is already too long a story for the course. So you might recall from school how to compute the determinant of a 2 by 2 matrix. So does anyone who didn't study information systems remember how to compute the determinant of a 2 by 2 matrix? Does anyone remember hearing the word determinant in school? Can you please raise your hand if you did? So that's basically all of you. Okay, and any guess? A, B, C, D, yeah, that's good. Maybe put in, maybe reorder the letters and put in a minus sign at one point.
AC minus B, AD minus B.
Yeah, exactly. Yeah, but that's the right approach. Just do it, and at one point you will be right. It's better than not doing it, definitely. So yes, so also, I mean, it's just something you can remember or you don't remember. So to compute this determinant, you need to multiply these two and then subtract these two from that. And you might also remember if you have a 3 by 3 matrix. So this A, B, C, D, E, F, G, H, I, that there was something like called Zarus rule. At least that's something that I learned in school, that you have to virtually extend that B, E, H, and then you can do the same thing by computing these. Oops. No, I'm a little bit off there. Computing these products and adding them and subtracting from that the products in the other direction. So maybe remember that for 3 by 3 matrices. That's as much as I want to tell you about determinants. The problem is there is a real, so one can of course compute determinants for larger matrices, but then one also needs to define what one actually means by that. And there is something called the Leibniz formula for determinants. But the problem with this formula is that it involves notions from group theory and permutation groups and so on. So it's in the script. It's the formula. That's a formula that one cannot really explain if one doesn't explain a lot of other things first. So you can sleep at peace because you know that this formula exists, so you don't need to worry about, but a determinant for larger than 2 by 2 or 3 by 3, I don't know how to compute. You can sleep in peace because there exists a formula for that, but the formula is too involved to actually cover here. So so that's why this is not very useful. also this formula, if you actually compute determinants, then you actually use some tricks and so on. So that's also not the formula that you necessarily use to evaluate determinants if you're forced to do that by hand. If you have a computer, you can just, for example, in MATLAB, use the command det a, and then you get the determinant. If it is defined for the matrix R, that means if it's a square matrix. So for us, the only thing, it's really not that important. But I just wanted to let you know what I mean by this, or what the world means, not only me, means by this symbol. So it takes the covariance matrix and returns a single value. There are interpretations of determinants that are something like volume, but this also means that you need to understand a little bit how columns of matrices make up vector spaces, and how, in this sense, this can be something like volume. So just view it as some constant in the probability density function that needs to be evaluated, and is essentially just a single number. There's something to add about determinants? No. Yeah, but now we have, although some things more in depth and others more in more superficial, discuss all the ingredients of this formula here. Is there something in this formula that you feel we have not addressed? No. What we haven't really addressed is its meaning, of course, and this is what we will do now then. And I think from now on, I think for calculus, for the basics of calculus, I will make an additional video, so we will not discuss that here. So from now on, we are really onto proper GLM theory and no more mathematical preliminaries. Okay, so let's assume now that we are all happy with something like this, although you might not be happy with the left-hand side, 2 pi minus n 1/2, determinant of sigma to the power of minus 1/2, exponential function of minus 1/2 x minus mu transpose sigma inverse, and x minus mu. So what you're not quite be happy with is what I'm writing actually here on the left-hand side. So here I use n for normal distribution, which is of course confusing because I always say Gaussian, but that's just how it is. So that's n. X is the random variable that we're interested in. So we're still in probability theory. The semicolon I put there in order to not put what some people do, put, for example, a bar there, which then always looks like some conditioning statement. And what I put after the semicolon are parameters of this probability density function. Yeah. So what this is supposed to tell you is that we're talking about the normal distribution or Gaussian distribution probability density function. This is how we call our random variable for which we define probability density values. And these are the parameters of the Gaussian probability density function that we are currently interested in. And to make this now more concrete, we first look at what this actually means in the univariate case. Univariate case, by which I mean that x is a scalar, mu is also scalar, and sigma is a positive definite matrix. And one of the shortcomings of this whole course is that I don't really explain positive definite matrices, but you can, for to again sleep well, you can think of positive definite matrices roughly as the extension of positive numbers. It's very rough, but at least it's something that helps to also relate it to the univariate case, because in the univariate case, sigma is a positive scalar and actually is usually called sigma square. Where the square comes from, that will be clear when we look at bivariate things. But so in the univariate case, the sigma is actually usually denoted as sigma square, which is larger than 0. This is actually already quite important because the variance and covariance parameter of a Gaussian are never 0. Yeah. That's important. That it can be a source of confusion because it's just not defined. A Gaussian with variance 0 is just not existing. Yeah. So in the univariate case, of course, the most important thing I forgot so far is that n equals 1. So what do we get for our probability density function then? Well, we have now something like this because our big sigma is called sigma square, and we get 2 pi to the power of minus 1 over 2 times the determinant of our sigma square. And yeah, I really didn't define what the determinant for a scalar number is, but you can view it as the extension of the absolute value. The determinant of a matrix with a single, that's actually quite true. The determinant of a matrix with a single value is just that single value. So what we actually get is sigma square to the power of minus 1/2. And then we get x minus 1/2. Here we get the inverse of sigma square. So that's because we are now in the scalar case, just 1 over sigma square. So we can put that up front already. And then we have a scalar minus another scalar transposed. What's the transpose of a scalar? A what? Itself. Yeah, itself. Sorry, I just it's itself. So if you have 2 transpose, that's just 2. So we have the transpose of something with itself, and then multiplied the transpose of a scalar, which is just itself, and then multiplied again with that. So that's the same thing that you are familiar with as square. So we are almost where you should maybe or maybe not see something familiar here. The only thing that we can still change is this minus to the power of 1/2. So that's square root, of course, but we can actually, because we have the same exponent here, we can put this in there. Now we get rid of that. And then we have to the power of 1/2. And so we have minus to the power of 1/2. So that's 1 over to the power of 1/2. And to the power of 1/2 is square root. So we get 2, 1 to the, yeah. So, yeah. So that's the univariate Gaussian probability density function, as I also wrote it last time. So the multivariate Gaussian probability density function is just the extension of the univariate case. I hope I didn't forget something. So now let's have a look at what that actually means. So the curve that is described by this, so this is now our x. The curve that is described by this term actually has this bell-shaped form. This part here This is there to make sure that the whole function integrates to 1 over the real numbers, because we want a probability density function. Yeah. So the only thing why this is somewhat important is because the action. So if you if you change the x value, then you actually get different values here for what we now call nx mu sigma square. And then, of course, you know the effects of changing the expectation and the variance parameters. So let's say this is now our mu. So you know that the expectation is where a Gaussian is centered. So let's say that is mu equals 3. Now, if I come up with another univariate Gaussian where I change the color and say mu equals 2. Where is this? So what do I have to draw? What changes? The mean, yeah, exactly. So the expectation value changes. I will always call it the expectation. Actually, I call it the expectation parameter. I will at one point come back to it, because you should never confuse a mean that you compute on data with the expectation parameter of a Gaussian. Although the expectation parameter of a Gaussian is often also called the mean. I will come back to that at one point, but not now. But you know that if you have the same variance, then essentially the expectation parameter determines where this univariate Gaussian is located on the x-axis. Yeah. If I only change the variance, so let's say, so of course I should now write up the rest. So here first our mu was 3 and our sigma square, let's say, was 1. Now if I increase the sigma square parameter to, let's say, 2, what happens with the black one? Yeah. It gets wider. You also know that from psychology, because you had this thing with the 63% and the 95%. So you are familiar with that, although it was maybe introduced differently. So if we have the same mean, so for here, let's say mu is still 3, then we need to get wider. So maybe, I mean, it's not really wide, but we get something like this. Yeah. So these parameters in the univariate case you are fairly familiar with. So the mu determines where the whole thing is located, and the sigma square determines how wide or narrow the thing is. Yeah. Narrow means a small variance parameter, and wide means large variance parameter. Now let's also revise what we discussed last time already. So this is a probability density function, and we made some fuss about probability density function last time, so at least I made some fuss. Lena then was completely relaxed and said, it's just how you sample from it that's important, and this is actually the case. So this is now our probability density function, nx mu sigma square. How it exactly looks depends on the values of mu and sigma square, but what the intuition that you can get from that is, if you now would take samples, so you have a random number generator and you want to take samples, and let's say mu equals 3. And I say here we have, let's say 4, 3, here we have 2, here we have 1, and here we have 5. By looking at the function, what do you think is more likely? That I sample a value of 0.01 or I sample a value of 0.01? What happens more often? A or B? Who is for A? Who is for B? Good. So you understand this. So you, if you sample, you would get a value here quite often. So here you sample many values if you would sample from it, and here you would just occasionally sample something. Yeah, that's as much of an intuition you actually need from that. But again, don't be surprised that here this is not 1 or something for every Gaussian, because it's a density. Yeah, so really the probability is defined for intervals on the x-axis. But yeah, so that's essentially I think what we should discuss about the univariate Gaussian, which also means that we have to discuss bivariate Gaussians, and we have a little bit of time. So let's talk about bivariate Gaussians. Because bivariate Gaussians are important because they are those that you usually see and can readily visualize. So in the bivariate case, n equals 2. So what we actually have is that our x is now a 2-dimensional vector, our mu is also a 2-dimensional vector, and our sigma is a 2x2 matrix. Yeah? And so let's look maybe a little bit closer into our x. So x has now 2 components, x1 and x2. And of course, our multivariate Gaussian probability density function still returns for each x, for each x, so for each input, a single value. Yeah, so this gets mapped onto n. One can write it a little bit more in detail if one wants to. On a value here. So our mu, of course, also has 2 entries, and our sigma has now, and I will just write them down for now, has 4 entries. Yeah, one thing I actually forgot to tell you about sigma. But that's fine for a second. So now, and this is why I stress this function bit that much, this value is still just a scalar. Yeah. Now one, of course, wants to visualize that, and there are different ways to visualize that. One way that I don't prefer actually is to do a 3D plot where you put x1 on one axis, x2 on another axis, and then you do something in 3D that looks something like this. Yeah, so you think of a bell-shaped thing in 3D, although it's a little hard to see actually. I don't like that much because one always gets confused about 3D or 2D and so on. So this is a 2-dimensional Gaussian. If one wants to visualize a 3D Gaussian, that actually looks quite funky, and we will not do that. So the way that I prefer to visualize 2D Gaussians are as follows. You take your x1, you take your x2. Then this thing says that for each x1 and x2 you get a single value back. Now you can encode these values for each x1 and x2 in terms of some color. And let's do that. So I will now just draw something. So I'm drawing some yellow bits here. Some orange, oops, some orange around that, oops, and some red, of course. And then let's make the outside blue so that it looks like in the script, so that would be the blue bit. Of course, it looks much nicer in the script, but this color now has meaning. So blue would be low values, and then it's a heat map if you want. So yellow would be high values, and our orange and Jesus, why does one always have to go back to that? So, and that actually represents a scale. It represents the positive real numbers. Yeah. So what you then see here in this plot, and you see these plots everywhere when you talk about bivariate Gaussians, is that certain points in this two-dimensional space, so in this R2 thing, so basically the set of all values for x1 and x2, get allocated quite high probability density, and others get allocated relatively low probability density. Yeah. Now let's first appeal to your intuition again. Let's call this dot here, maybe I should call it dot, not x, so then it's less confusing. Let's call this dot xa1, xa2, and let's call this dot here xb1, xb2. Yeah. So we have two dots here, and they are defined in terms of their two coordinates. So for example, if we have here 5 and we have here 1, then this would be roughly the dot 5 and 1, and this could be something like 2 and 2 or something. Now, from what we discussed about probability density function for the univariate case, what do you think is more likely, that we sample XA or that we sample XB? So who thinks it's more likely that we should sample XA from this probability density function? Who thinks it's more likely that we sample XB? Everybody thinks that it's more likely that we sample XB, and this is completely right, of course. So that's the intuition you should have when you, bless you, if you look at sampling graphs from such a plot, then what you should think is, okay, if the distribution, if the probability density function of the Gaussian that we're interested in looks like this, then it's much more likely that I sample values around here than that I sample a value here. So that would happen only rarely. So here you get really many samples, and then it thins out as you go to locations in space where you have lower probability density. Yep.
Is it often that this figure is going to be in the center of the graph?
That's actually a good question. It usually it appears to be the case that whenever you see this picture, it's in the center of the graph. What actually, and I think we have to leave some of that for next time. The center of this is, of course, the place where you have the highest probability density. Now, if you think again of this, the highest probability density here was specified in terms of this mu. And this is exactly the same for the bivariate case. So the center of this graph is, again, our expectation parameter. So it's this mu1, mu2. And then it, regarding your question, that depends how you put this on a number of things. So if, let's say this is 1, 2, 3, 4, 5, and this is 1, 2, 3, 4, 5. If in this case, for example, have a Gaussian that is centered on 3, 3, then the center will be here and it will appear largely in the center of the graph. Now, if I have a Gaussian like with a mu, let's say 5, 1, so the first, so that's x1, that's x2, the first is 5, the second is 1, then it will appear like that. Now, if you have in addition a fairly small variance and covariance in terms of the covariance matrix, which we will talk about more next time, then you might actually have something like this. And then it's clearly not in the center of the plot. However, if you are interested in plotting this, what usually will happen is that you actually focus on there, and that's why it always seems to be in the middle of the plot. But it's not that it's always in the middle of something. Okay, other questions about as far as we got here? No. Good. So, but this is, I mean, we achieved quite some stuff. So I think we will start then next time with rehearsing a little bit this and maybe filling in some details regarding the covariance matrix. But then we, I think, are really in the position to finally, and this is why we're doing the whole thing, is to clarify what this epsilon, what that means and why it's so important and why I'm doing all of this stuff and you are listening to it. Good, then see you on Thursday or next week.